There are four classifications of alkenes. Alkenes are classified based on how many carbon chains are connected to the two carbons in the double bond. So if you sort of think of each of these carbons and these double bonds as places that other carbons can be attached, the two carbons at the end there, and just putting a dot to emphasize those, then you can imagine having just one carbon branch attached to one of those dots. Just one carbon chain coming off of the double bond. And that double bond is classified as monosubstituted. Remember, a substituent is another just a fancy word for a branch. And so if you have one carbon branch coming off of the double bond, then it's monosubstituted. If you have two coming off, now here I'm going to put them both coming off of this same carbon, but the second one could have come off of the other one. If you have two coming off, then that is described as being disubstituted. If you have three carbons coming off of the carbons in the double bond, that's described as being trisubstituted. And if you have four, that is described as being tetrasubstituted. Okay, so the significance behind these different classifications is they tell you the stability of the alkene. So the monosubstituted product the monosubstituted alkene is the least stable. And the tetrasubstituted alkene is the most stable. The more carbons you bond to the carbons in the double bond, the more stable the double bond is. Now, if you want to think about why that is, you would want to be able to visualize how that pi bond is forming. The pi bond is forming because of parallel p orbitals on those two carbons, right? Remember, let's finish. So you have parallel p orbitals on the two carbons in the pi bond, and that's what's giving rise to the pi bond. So remember, you have two types of bonds. You could have sigma bonds. That's always the first bond you form. You get those when two orbitals overlap without any interruptions. They just overlap there. Remember, each of these orbitals is a standing wave. And just like if you were to create two waves in water, if they were to finally come together, when they do reach each other and come together, they add to create a bigger wave when they come together. And so likewise, these standing waves that are the orbitals, those bleed into each other and create a bigger orbital. And that's what we think of as a bond. So if they come together, they bleed into each other without any interruption, then it's a strong bond, and so it's a sigma bond. There's one other way. That's always the first bond that you form. There's one other way to form a bond. That's with parallel p orbitals. So in this case, the lobes, the top and bottom lobes, do bleed into each other. But you'll see that in the middle, that overlap is interrupted. So when you get that type of an overlap, that type of waves overlapping and bleeding into each other, that's a weaker type of bond. It's called a pi bond. So that's every bond after the first bond is formed by that overlap, incomplete overlap of two parallel p orbitals. So we have those in these alkenes. Anytime you have a pi bond, that second bond is coming from those two parallel p orbitals. Now those orbitals can interact with the sp3 orbitals on the adjacent carbons. So these sp3 orbitals, you have a few of them, and they point in different directions, but they ultimately give you the tetrahedral shape of that sp3 hybridized carbon. Two of those orbitals will not overlap very well, but one of those sp3 orbitals will overlap a little bit with half of the p orbitals. Now you might see a little bit better in this picture here. So let's just zoom in. We're going to zoom in on just one half of these p orbitals and one of the sp3 orbitals. So notice, this is one of the p orbitals in the pi bond, and you have the sp3 orbitals here, giving you that tetrahedral shape. Now this one in front is pointing out at us the one in the back is pointing away from us, but this one here is in line with the page, and so are the the orbitals of the p orbital. And you notice that the one that's in the page kind of bleeds into and overlaps with the p orbital. So that overlap allows the electrons in the p orbital to spread out. It spreads out into this orbital. That spreading out between 1/2 of a p orbital and half of an sp3 orbital, that's hyperconjugation. So hyperconjugation is when 1/2 of a p orbital kind of overlaps with an sp3 orbital and bleeds into it a little bit. Now notice, whenever you spread charge out, it becomes more stable. And so, when this p orbital bleeds into this, the electrons in this p orbital bleeds into a little bit, that sp3 orbital, the electrons spread out and that stabilizes the molecule. So if you can only do that with one carbon, that's not so stable. But if you can do that with more than one carbon, so the electron density that's here bleeds into one sp3 orbital at the bottom and another sp3 orbital at the top, that's more stable. If you have the sp3 orbitals on the bottom, the top, and then another bottom, well, that's 3 places where this electron density can spread out. It spreads out even more, and that makes it even more stable. And it's more stable because when it's spread out, it can exist that way more often. It's more likely that it will exist that way, and so it will occur more often. And so we see that as being more stable, as lasting for a longer time. So if you have 4 carbons there, then the electrons are able to spread out into those sp3 orbitals in 4 different ways, and it becomes the most spread out, and so the most stable of all of those pi bonds. So the crucial thing to remember is that these double bonds can be classified as monosubstituted, disubstituted, monosubstituted, disubstituted, trisubstituted, and tetrasubstituted, based on the number of branches that are connected to the carbons in the double bond. Okay, and that's significant because the more carbons that are bonded to the double bond, the carbons in the double bond, the more stable the alkene is. Okay, so let's try to classify some different alkenes as monosubstituted, disubstituted, trisubstituted, or tetrasubstituted, and let's also make a note of how stable they are relatively as we do that. So first, just put little dots at the end of the double bond, and think how many carbons are coming off of those dots. Now we're not going to count the double bond itself, just carbons, sp3 hybridized carbons coming off of that. So we have an sp3 hybridized carbon, 1, 2, 3 of them. So we have 3 sp3 orbitals that the p orbitals and the pi bond can bleed into. So this is going to be trisubstituted. So that'll be more stable than mono or disubstituted, less stable than tetrasubstituted. Okay, for B, same thing. Put a dot at the end of each of the double bonds. Put a dot for each of the carbons in the double bond. And then think about how many carbons, how many sp3 hybridized carbons are coming off of that. So we've got 1, 2 here. So we have 2 sp3 hybridized carbons attached. And so that's going to be disubstituted. Which means that the electrons in the p orbitals will only be able to bleed into 2 sp3 orbitals. So that's more stable than if it were monosubstituted, but less stable than if it were tri or tetrasubstituted. For C, put little dots where you have the p orbitals on each end of the double bond, and then think about how many sp3 hybridized carbons are bonded to that. We have it in one place, a second place, and a third place. So this has sp3 orbitals in 3 places. And so this is going to be trisubstituted. Now you may wonder, wait a second, this carbon here is the same one. How come we're counting it twice? And that's because it's connected to the carbons in the double bonds twice. It's sort of like having two holes in a bowl, right? This here's our bowl of electrons, and the more the water can leak out of this bowl, the more stable it's going to be. Well, it doesn't matter where the water goes. It doesn't matter if the water goes to the same place twice. It just matters that there are two holes for the water to leak out in. And so that helps to spread the charge out more. So this is trisubstituted. The electrons are able to leak out of those pi bonds in 3 different ways. And so that is going to be more stable than disubstituted or monosubstituted, but less stable than tetrasubstituted alkenes. Okay, for D, we'll put dots for where we have the carbons in the double bond, and then we want to think about how many sp3 hybridized carbons we have that those pi electrons can leak into. We've got 1, 2, 3. So that there are 3 sp3 orbitals, 3 places where sp3 orbitals can allow the electrons in the pi bond to leak into them, and so this is going to be trisubstituted. So that's more stable than a monosubstituted or disubstituted alkene, but less stable than a tetrasubstituted alkene. And finally for E, just put those 2 dots at the end of the double bond for where the carbons are in the double bond, and think about how many sp3 orbitals are there attached to that the p orbitals can leak into through hyperconjugation. Well, there's only this one, and so this is monosubstituted. There's just one sp3 orbital that the p orbital electrons can leak into. Right, we have those p orbitals here. That's what's creating the second bond, the pi bond. And we have an sp3 orbital here. And the electrons are able to leak into that. The electrons in this bond are able to leak into that a little bit through hyperconjugation. That lets the electrons spread out, and so that stabilizes them a little bit. Okay, again, through this hyperconjugation, the p orbital and one of the sp3 orbitals overlap a little. So you'll want to be able to look at alkenes and quickly tell how substituted they are, and based on that, how stable